Good morning, everyone. Welcome to our beautiful channel Concept Raja. Okay, so at last video we have calculated the potential, okay, of a point due to a uniform ring. Correct? We have calculated the potential of a point and we have come up with a formula called minus gm by z. Okay, in the last video we have explained like how we have calculated that. Now our main goal is to calculate the potential, okay, due to a uh, sphere, correct, like solid sphere, like earth we consider as a solid sphere. Okay, to reach to accomplishing the solid sphere, okay, we need to go with the first ring, then we calculate the spherical shell or hollow sphere, and from the hollow sphere we'll go to the solid sphere. Okay, so and what we're gonna do here, we're gonna use the mathematical technique called integration. Correct, like mainly we will use the mathematical technique called integration. So so now first thing, like what we can do here is that from the mathematics, what are the things we need here is that we're gonna apply integration. Okay, and we're gonna apply some of the trigonometric techniques, trigonometry. Okay, very basic trigonometry will apply, and some geometry. Okay, to achieve that. Now integration, what we are doing, like last video I've already discussed, very detail that the hemisphere, like our main goal is to accomplish the uh, solid sphere. Solid sphere can be made using of uh, multiple uh, thin cell or hollow spheres, correct? Like if I have a small, I can calculate the potential of hollow sphere, then I can keep adding the hollow sphere, next to next, like this. If you just imagine, okay, I'm adding the hollow sphere, and this hollow sphere will make a solid sphere. Okay, now but the hollow sphere how I'll make, I'll have a ring, correct? I calculate the potential of a ring. From that, if I if I calculate, if suppose I have a potential of a ring, now I want to calculate the potential due to the potential of a hollow sphere, is that hollow sphere I can make by small ring if I add it. Okay, just imagine, see the picture here I drawn here. Okay, so if you keep adding the pictures, like this picture, if you see here, I'm keep adding the different rings, okay, one by one, and I'm creating this. So this is like a infinity rings will be there. Okay, and we can see here the different size. Okay, all rings will have a same center point, like it is passing through the all the ring center, and all rings having a different radius. Ring size is different. So what are what is changing here? Size is changing, ring size is changing, correct? And so size changing means ring mass will change, so each ring mass will different. Okay, now we know, if I know the ring mass, okay, from that we can easily calculate the distance, the potential of a point from that ring. Like what is the potential of a point from the ring? Now, for example, we have taken one of the ring here. Just see here, one of the ring I have taken it here. How we have taken? If you see that, just imagine. So just this is my hollow sphere, correct? How can I make this hollow sphere? I can have, see, I can have a multiple rings, correct? One ring here, after that a ring, one ring. Like it is not like that much gap will be there. Like if I keep adding the rings, okay, and with giving very less space between them, it's like infinity ring. If I keep adding that, then it will become a hollow sphere, correct? We can see this from this picture. We can make it very clear. Now, so what is happening? So from here, if I draw, like from here, I'm drawing a ring, then I'm drawing a ring like that, correct? So this is the radius of the. So this is the radius of the hollow sphere, correct? So now if I change it, like if from here, from here I'm starting, okay, now if I'm going from here, so like from, if I this is the angle I have taken, correct? Like suppose this is the theta angle I have taken, and so if I vary theta from 0 to pi and I add infinity ring between them, then I can create a hollow sphere using the rings. Okay, so before deriving this, like what is the potential of a point due to this hollow sphere, okay, before deriving it, okay, I would like to give you the formula of the final formula. What is the potential? So now what is happening, like suppose this is the hollow sphere, correct? Now what is that point might be staying here outside the, it is the distance from the center is r. Okay, this is might be the case, point will be outside the hollow sphere, or there is a situation point must be on the hollow sphere, correct, or point might be at the inside the hollow sphere. Okay, so this is the distance r, correct, this case where point is on the hollow sphere. This is the distance r, correct, not this distance, sorry, I'll delete it. So this is the distance from the, okay, this this is the distance from the center. Okay, if point is inside the hollow sphere, then okay, what is the distance, like from here, this is the distance r, correct, for each case. Okay, what will be, and for all cases this is the radius of the, you know, so here if I say r is greater than a, here r is equal to a, here r is less than a, correct, this is a, r is less than a. For each case, like I'll write the formula here. Okay, derive the formula. So potential, I know always it is negative. This case, if mass of the ring is, mass of the hollow sphere is, or thin cell is m, then g m by r. For this case, as r equal to a, it will be g m by a, correct. And when point is inside the hollow sphere anywhere, okay, like r is less than a, that time also the formula for the, you know, potential of a point, like point is here for example, then it will be g m by a. Okay, so we can see that when point is outside the hollow sphere, then potential is, you know, inversely proportional with the distance from the center. Otherwise potential is constant, correct. So this is the formula, this is the formula, we'll get it after, but in this video our main aim is to how to prove that formula, correct, how will you know, achieve to this formula. Now, so first thing I told that I can make a hollow sphere by including you know, like infinity ring together. Okay, and integrating infinity ring together is the mathematical technique, is integration, we are using integration, correct. And see here I am just when we do integration, correct, when we learn about integration, that time we will, you know, get a great detail about that integration, how, what is the, how we'll do the integration, and how will you know, how, why integration is needed, correct. But here I'm not going to that detail, but I'm telling, like, I know like infinity ring I have to add it, and I have understood that, you know, I have to change it from theta, I have to take a theta angle, I have to change the theta from 0 to pi, correct. So if I change the 0 to pi, I can keep changing the theta, and I can keep adding the rings. Okay, and based on that theta, ring size will be different. And what will differ there, if you see that ring, each ring have a separate distance, correct, that z will change, correct. So here, from here z is this much, from here z will be this much, from here z will be this much, correct. So z will change based on the position of the ring in the hollow sphere. Okay, and we know the, you know, these are the all uniform rings, correct, and we are calculating uniform thin spherical spheres. So uniform ring, we know the formula is minus g m by z. Okay, for ring, so here I explain for the three situation, correct, in the hollow sphere. One is r is greater than a, r is equal to a, r is less than a. But for ring, r is like, there is no, you know, inside or outside, correct, like both sides will be like outside for the ring, so it will be like a g m by g. G is the distance from the ring to the point. So this is the potential of a point due to ring, correct. This is, we have already derived. Now I have to see I have to check like how we can derive it. Okay, so now here see what are the variable here. So one is variable theta. So from here, this is the center of the, you know, this sphere. Okay, this is the a is the radius of the sphere. Okay, if this is theta, this is a, then what should be this will be a sine theta, correct. Okay, and now uniform spherical, say uniform means mass is uniformly distributed across the sphere. As it is a hollow sphere, so mass will be distributed only at the surface area, correct, surface area of the sphere. So what is the surface area of the sphere with a, you know, a radius a is 4 pi a square. This ring, this sphere mass is m, area sorry radius is a. Okay. Now what is the mass? Mass is m, correct? So mass per surface area is nothing but the m by 4 pi a square. Okay, now I have taken a very thin, okay, very thin. What is this thickness? Thickness is just this thickness is nothing but the very thin, correct? And where I say this is, if this is theta, if I draw this, correct, like, you know, this from the same angle, if I draw the another line, so in the theta angle, okay, so this thickness, for example, this thickness is very thin, correct, dx. Okay, what is this thickness then? So if I have a angle theta, okay, and this is the arc of a circle, correct? We know this is, if this is the r, then it will be r theta, correct? Based on that, I can say that this thickness is nothing but the a is the radius, okay, a is the radius, okay, and d theta is the angle, correct? In d theta, angle d theta, we have taken another strip of that, and we are making this ring. So this is, there is, this is the ring, for example, this is a d theta is the thickness, correct, and the radius of the ring is a, correct. Then what is the area of this ring? Area, I can say, if I cut this ring and I can open like a, you know, rectangle, it will be become a d theta, sorry, this is a d theta, okay, and the area, sorry, the radius of the ring, radius of the ring is a sine theta, correct. We calculate radius of the ring is a sine theta, but radius of the sphere is a, so this is a sine theta. So now area is nothing but the a square sine theta d theta. Okay, I hope up to here it is clear. If it is not, you can pause your video, or you can, you know, or just go go back and again check that. It's very simple, correct? I have taken a very thin ring, created a thin ring with the thickness is a d theta. How I calculated a d theta? This is the, you know, the portion. So now the whole ring, if I consider whole ring, the mass per area is this, correct? And this ring mass I am taking as a dm. What is that mass? Dm. Because in physics, I always I last video also I told that very very small thing will represent it as a d, small d. Correct? In calculus we do it like a d theta, very small change. Something is changing. Like we first you have delta, then you have a d is a very small. Like d theta tends to 0. Okay, or dm, like here the mass is dm. Now the mass of this ring is dm, mass per area, and as it is uniform, both will be equal, correct? And what is the area for that particular ring is nothing but the a square sine theta, sorry, it is the 2 pi a sine theta. So this is 2 pi a square sine theta d theta. Why 2 pi a sine theta? Because if you open this is the perimeter, 2 pi a sine theta. Sine theta is the radius, 2 pi a is the perimeter into this height, correct, a d theta. Now if I cancel this, so here I'll have a 2 pi square will get cancelled 2. Now I get dm equal to m sine theta d theta divided by 2, m by 2 sine theta d theta. So now we can see here, correct. First we have already observed rings are different size, so rings, the radius of the ring, suppose radius of the ring is r, then it is like a sine theta. So you can see that r is changing, r is not fixed, correct, r is changing with the theta, because I told like from theta 0 to pi, if I do, theta will change, correct, theta will change as soon as ring size will change. So this is proof, ring size is changing, correct, radius is changing. Now dm is changing because dm also depend on the sine theta and d theta, correct. As sine theta changes, dm changes, and this is the relation, this is the function I have created, correct. The dm, the function of dm with respect to sine theta d theta and the m. Okay. Now what the things will change? Z will change, correct. Another thing is changing, that is z. Now go to the next slide. So what is changing? Z. Z is nothing but the distance from that ring to the point. So okay, let's so I'm just drawing that part, like this is the point A, Okay, like what is the point A? For example, this is the point A. This ring I have considered, correct? One arbitrary ring I have taken on the angle theta. Now from point A to point B, correct? Like so this is the distance. So considering this ring, this is the distance point P, and from here we are drawing a line. So this is the area. Sorry, this is the uh, what you call the line. Okay, joining to the line joining to the point P. Okay, going through the ring. This one. So and this is the angle theta. Correct. So and this is the ring, somewhere is the ring, what you call the distance, correct, like the distance of the sorry, the center of the ring is passing through the, so that what I'm going to say here is that the line passing through the ring axis, okay, passing through the ring center, okay, axis, and the point is on the axis, and this is the distance between the, so this is the z, correct, and we know the formula for the potential, okay, because I have taken a small ring, so the formula for the potential is dv, small potential due to the small ring with mass dm is nothing but the minus g dm by z, correct. This z is the distance. Now but z is not fixed here, correct. For one ring I have taken the z here, but z is not a fixed here. Z is also changing. Now let's say how I can represent Z with theta or something. So from this, uh, so this is O, correct. From this triangle we can use the cosine rule, and I can get it like a Z square equal to, this distance is R, this distance is A, this is the radius of the hollow sphere, correct. I can write A square plus R square minus 2AR d cos theta. This is the cosine rule, correct. We'll gonna learn all the things. Okay, so this is z square equal to a square plus r square minus 2ar cos theta. Okay, now z is changing and theta is changing. Okay, other things all are fixed. So through the, I can do that, like if I differentiate both part with d theta, I can write d dt theta of a square plus r square minus 2ar cos theta, correct. Now as I am differentiating, his z is not a constant, correct. Z is a changing, because I saw, correct, distance. See here z will keep changing, correct. Z from here is z, this is different z and z, so z is a variable here. Now so what I can do, I can partially differentiate z with dz, correct, and then I can do that dz by d theta equal to, so this is constant 0 constant 0, so I can write minus 2 ar d of cos theta d theta. So here I can write 2z dz by d theta, okay, equal to minus 2ar plus 2ar cos theta is minus sin theta, so it will become plus 2ar sin theta. So I'm getting one another relation is that 2z dz equal to 2ar sin theta d theta. Okay, and the last slide we have seen that dm equal to m by 2 sin theta d theta. Okay, now nothing is, what we'll do, we're gonna replace all that thing here. Now what the small potential due to that ring I'm getting is that minus g dm by z, correct. So this is the, the ring mass is dm. So now I replace dm here, okay, minus z dm is nothing but the m by 2, okay, z is g sin theta d theta. Now sin theta, so now I get it here, okay, sin theta d theta by z, correct. So I can cancel 2 and 2 can get cancelled, correct. Now I can this is the dv. So from here what I am getting, sin theta d theta by z equal to, okay, sin theta d theta by z equal to dz by ar. Okay, sin theta d theta by z equal to dz by ar. This is the equation I got it. So here dv equal to minus gm by 2. I can write this sin theta d theta by z equal to dz by ar. Correct? I can write it dz by ar, because see dz is the variable, because z is variable. Correct? So z is changing here. R is constant, a is constant. Now this is the situation I got. Okay, now in this video I have already discussed, we have gonna consider three situations. Correct? One is r is outside, or r is inside, and r is on the surface, is r equal to a. Correct? So from here what we can see, now let's consider r is, so I'll consider the case 1. Okay, where r is greater than a. What is r? If this is the sphere, what is r? R is distance from that point, from the center. So if this is the center of the sphere O, then this r is, suppose this is the point P. Okay, so r is nothing but the distance from the center to the point, and this is a sphere, this is a hollow sphere. Now, and what is a? This is the a, correct? Like if I take the radius is a here, this is a, this is also a. Now case 1, r is greater than a, that means r is outside the sphere. Point P is lying outside the sphere. Okay. Now consider when r is greater than, so suppose now how so before that integration, what I told, that I will vary the theta from I taken an angle theta, and I taken a ring, arbitrary ring here, correct? Then I am calculated all these things for a particular ring. Now I come up with that, for that ring we get a the potential of dv equal to minus gm by 2 ar into dz. So you can see that potential is changing. I have to integrate in the dz, I have to integrate in the distance. This will be remain constant, because a is constant, r will be constant for the particular point. Now if r is, so now I have to change the theta, but I don't see any theta variable, correct? Now if theta equal to 0, theta equal to 0 means this point will lie here. Now this will become your a, correct? Okay, now what is the distance r? This is the distance r. What is z? Z is nothing but this distance, correct? This is the z, that from the sphere to the point, that is the z. From here this distance is z when theta equal to 0, like for theta equal to 0, this is the case. Okay, now how z, if theta equal to 0 to pi means, when theta equal to 0, what is z? Z is equal to total distance is r, and this is a. So when theta equal to 0, z should be r minus a. Clear? Okay. But when theta equal to pi, what will happen? Z from here to here, total distance will be z. Correct? From here to p. Now when theta equal to pi, z is nothing but this is a and this is r. So r plus a. So if I change, because now the variable is dz, here now theta is not there, because I replace theta with the dz. Now when I have to, now case1, what I have to do, see my main aim is to now integrate, correct? Integrate all the integrate the rings with the different size, and I have for the different size I have a different distance from the point, then I have the different mass, and so all that thing I have algebraically I have solved, and I find out this final thing is that dv equal to minus gm by 2 ar dz. I have to integrate, correct? So v equal to nothing but I will integrate all that thing. What is the range, correct? I have to integrate, like this is a definite integral I'll do. I'll do the integration from theta equal to 0 is nothing but the r minus a, because this is variable is z now, dz. So r minus a to r plus a, correct? And I can write minus gm by 2ar into dz. Here everything is constant, correct? V equal to minus gm by 2ar. A is constant, r is constant, vm2 is constant. Now r minus a to r plus a, okay, dz, and the integration of dz is z, and so I'm just writing the integration thing gm by 2ar. Here I can write z of r minus a to r plus a, and finally if I integrate I'll get like 2ar. So here I put the values r plus a minus r plus a, and r will get cancelled, 2a and this a will get cancelled. So final answer is minus gm by r, correct? In the last slide I told if z greater than, if p is outside, then this is the formula we'll get, correct? We got this formula. What is r here? R is nothing but the distance from the center to that particular point. Okay, fine. This is the case 1. I think this is, hope this is clear. If not clear, please recheck the video again and again and then try to understand. Now case 2, what is case 2? Case 2 is nothing but r is less than a, correct? Okay, case 2 is, sorry, case 2 I told r is equal to a. Now based on the outside formula, what I can do, I can write minus gm by r. Here r equal to a, so I can write minus gm by a. Now case 3, r is less than a. What is that? Like, let's draw again. Okay, now this is the point, suppose point p is here, for example. Now this is my distance r, correct? Whole distance, this total distance is a, this is r. So what we check the from the, so what is z? Z is from that sphere, you know from the sphere like surface to the point. So actually this distance should be z. Okay, so let it make it more clear actually. Okay, okay, this is the center. For example, I'll draw like this. Suppose this is the point P. Okay, this distance, correct? This from center to the point P is the distance r. And what is z? Because we are doing the, varying the z is varying, correct? Z is nothing but the from the surface of the sphere to that particular point. So this distance is z. This distance is z, and obviously the radius is a. This total distance is radius is a. Now when theta is changing from 0 to pi, correct? When theta is changing from 0 to pi, what will changing? When theta is 0, okay, when theta is 0, like it will come here. Then what will happen? How the z is changing? So now when theta equal to 0, that time z is nothing but the a minus r. Total is a minus r. When theta is pi, okay, this is theta equal to 0. When theta equal to pi, then what will happen? This is a, z is nothing but the a plus r, correct? Clear? When theta equal to pi, it will come here. So this point, if I here, and theta pi means it will come here. So what will happen? From here to here, correct? What is the distance? Correct? So you can do that. This is r and this is a. This is r, this is a plus r. This is the distance. Okay. Now we will do the same integration, correct? We have the same, like v equal to some dv, only the range will change here. Okay, what is the range? Minus gm by 2ar, okay, a minus r to a plus r dz. Okay, now this will become minus gm by 2ar. Here I'm just directly writing a plus r minus a plus r. So here a will get cancelled, so it will become minus gm by a. So when point lies inside the sphere, what I'm getting the formula? V equal to nothing but the point gm by a. So the final, we have already tell the formula. So now the if I draw the graph, correct, potential graph, like how the potential varies for a sphere. Suppose this is a sphere. Potential on the negative side, correct? We have explained why it is negative. So and for example, this is the radius, correct? This is the radius a. So this is a minus a, this is plus a. So potential will always on the minus a up to where? Up to the surface. So this is the potential. Potential is minus gm. So this is a constant, correct? Potential is constant. And when the outside, this is inside, v inside. Then v outside, it is minus gm by r. Now this distance is r. When r is up to a, potential is constant. From here it is 1 by r. 1 by r graph is like this. Okay, so this is the potential due to a point, okay, uh, potential due to a potential of a point due to a hollow sphere. Okay, I hope this video helps you to understand the derivation of that, and if you just keep see repeating the videos and see that. Thank you very much.